Module 10, Improper Integrals. 1. Infinite interval. Evaluate integral from 1 to infinity of 1 over x squared dx. Now, the formula is the following. This integral can be rewritten as the limit for b approaching infinity of integral from 1 to b of 1 over x squared dx. So let's rewrite it. Integral from infinity to 1 or 1 to infinity 1 over x squared dx equal limit for b approaching infinity of integral from 1 to b of 1 over x squared, by the way, becomes x to the power of minus 2. We simply translate x from the denominator up to the numerator. So x to the power of minus 2 dx, which is x minus 2 plus 1 over minus 2 plus 1, or minus 1 over x between b and 1, which resolves into equal limit b approaching infinity of minus 1 over b minus 1 minus minus 1 over 1, which is plus 1. Now, as b approaches infinity, this entire term cancels out. 1 over infinity is 0, so the limit should be plus 1. Again, since limit of 1 over b or minus 1 over b doesn't change anything really, as b approaches infinity is equal to 0, hence what remains of the limit is plus 1, which is the answer. So this integral converges because it has a finite limit. Integral from 1 to infinity of 1 over x dx. Applying the same concept and formula, this is equal to limit as b approaches infinity of integral from 1 to b 1 over x dx equal limit b approaching infinity of 1 over x dx. This is ln x between b and 1. So limit as b approaches infinity of ln b minus ln 1. ln 1 is 0. ln infinity is infinity. So this integral blows up to infinity. This is the full solution. So it is ln x between b and 1 as b approaches infinity equal limit ln b for b approaching infinity, which is plus infinity. So it is a divergent integral. Why? Because it goes to infinity. It blows up. Integral from 0 to infinity of e minus x dx equal limit b approaching infinity between 0, integral between 0 and b, e minus x dx, which is equal to minus e minus x between b and 0 equal minus e to the power of minus b, minus minus becomes plus, e0, which is 1, as b approaches infinity. Okay, e minus infinity, as we replace this with b, or replace b with infinity. So e minus infinity is equal to 0. It approaches 0. Correct? Why? Because this is the graph of the exponential. It starts from minus infinity, very close to 0. Then it starts increasing. E0 is equal to 1 and climbs all the way to plus infinity. Hence, e minus infinity is 0. So this entire thing approaches 1. limit as b approaches infinity, minus e minus x between b and 0, minus e minus b plus 1. This becomes 0. You end up with 1. Integral from 0 to infinity, e minus 2x dx. Limit as b approaches infinity. Straightforward. Integral between 0 and b of e minus 2x dx equal limit b approaching infinity of, okay, so e minus 2x becomes minus 1 half e minus 2x between b and 0. So minus 1 half e minus 2b, then minus minus becomes plus, 1 half e0. e0 is equal to 1. So the limit for b approaching infinity, e minus 2b becomes e minus infinity, which is 0. Cancels all of that out. And e0 is equal to 1 multiplied by 1 half. So it should be 1 over 2. And this is the final answer. Minus 1 half e minus 2x between b and 0 equal 1 half. Determine the convergence of integral from 1 to infinity of 1 over x3 dx. Okay, so limit as b approaches infinity, integral from 1 to b, 1 over x3 dx equal, now x3 becomes x to the power of minus 3 in the numerator, which is x to the power minus 3 plus 1 over minus 3 plus 1. So x minus 2 divided by minus 2, okay, between b and 1 equal, now x to the power of minus 2 is simply 1 over x squared. Hence, limit b approaching infinity minus 1 over 2x squared between b and 1. This is equal to minus 1 over 2b squared plus 1 over 2. Limit b as b approaches infinity. Now, as b approaches infinity, this entire part becomes 0. You end up with 1 over 2. Now, remember something, that this is actually a p series. It has a form of 1 over x to the power of p, where whenever p is greater than 1, strictly greater than 1, in our case it is equal to 3, then this series, this integral, would converge. Immediately you can figure that out, okay? So this has the form of integral from 1 to infinity of 1 over x to the power of p dx. When we compute the integral, so we end up with minus 1 over 2x squared between infinity and 1, which is 1 half. So convergent, and it converges to 1 over 2. Integral from 0 to 1 of 1 over square root of x dx. At first, square root of x can be written as x to the power of 1 over 2, 1 half. Given that it happens to be in the denominator, you can move it back to the numerator by flipping the sign. It becomes x to the power of minus 1 half. Now, as for the limit, we know that for x equals 0, 1 over 0 blows up, correct? So we cannot find it like this. We need to go into the methodology of limits. So this is equal to the limit as x approaches 0 plus or 0 minus, okay, integral from 1 to a 1 over square root of x dx. This becomes limit as x approaches 0. Okay, so again, this is integral from 1 to a of x to the power of minus 1/2, which is equal limit x approaching 0 of this is x to the power of minus 1 over 2 plus 1, talking about the result of the integral, divided by minus 1 over 2 plus 1, which is over 1/2. So you multiply back in the numerator by 2, and this becomes, okay, limit of 2 square root of x, because this is x to the power of 1/2, between 1 and a, equal limit x approaching 0 to square root of 1 minus 2 square root of a for a approaching 0. A approaching 0, this cancels out. You remain with 2 square root of 1, which is 2. And here is the solution. So it is limit as a approaches 0 plus integral from 1 to a x to the power of minus 1/2 dx equal limit a approaching 0 plus of 2 square root of x between 1 and a equal 2. Divergent endpoint singularity. Okay. Integral from 0 to 1, 1 over x dx. It is equal a approaching 0 plus of integral between a and 1, given that 0 in the denominator blows up, like it makes it unsolvable. It blows up the entire equation. This is why we need to replace it by a and evaluate the limit as a approaches 0 of 1 over x dx. 1 over x dx, that's integral of dx over x, it gives us ln x, logarithm. So equal limit a approaching 0 plus ln x between 1 and a equal limit a approaching 0 plus ln a minus ln1 minus ln a. Okay, ln1 is 0, but ln a, which is ln 0 plus, is equal to minus infinity. Minus infinity gives us plus infinity. So the integral diverges and blows up. It's called an endpoint singularity. And by the way, why does ln 0 blows up to infinity? Given that this is the graph of the logarithm, which is, by the way, the reciprocal function of the exponential. So the logarithm starts from minus infinity all the way to, okay, it clips the x-axis at x equal 1. This is why ln1 is equal to 0 and goes all the way to plus infinity. We note that its domain of definition is equal to 0 plus infinity. So logarithms do not exist in the negative scope of the axis. Okay, so it's only available for x going from 0 plus, meaning after the y-axis to the right. Okay, from 0 plus, right after x equals 0, all the way to plus infinity. So limit ln x between 1 and a approaching 0 plus equal minus limit ln a approaching 0 plus, which is minus infinity, diverge. Evaluate integral from 0 to infinity of 1 over 1 plus x squared dx. Now, this is equal to limit as b approaches infinity, as usual, integral from 0 to b of 1 over 1 plus x squared dx. Mind you that this has a result, an answer of arctan. Okay, so the integral for 1 over 1 plus x squared dx gives us arctan of x. Let's check it out. So it is equal limit of arctan x between b and 0, which is equal limit arctan b or arctan infinity minus arctan 0 as b approaches. Okay, basically we filled the b with its value of infinity. So first, arctan 0, meaning what is the angle for which the tangent becomes 0? That would be 0. Why? Because tan is equal to sine of the angle divided by cosine. Sine 0 equal to 0. Cosine 0 is equal to 1. So gives us 0. Okay, but for which angle the tangent becomes infinity? Simply, it is for 90 degrees. Why? Because in such case, tan pi over 2 is equal to sin pi over 2, which is 1, divided by cosine pi over 2, which is 0. So equal to 1 over 0, it blows up to infinity. Hence, the angle is pi over 2. That's why it is 90 degrees. Determine whether this integral converges. So limit b approaching infinity, integral from 1 to b of 1 over x squared plus 1, which gives us again arctan x between b and 1, which is between infinity and 1. Okay, arctan infinity minus arctan of 1. Now, first, arctan of infinity, for which angle the tangent becomes infinity? For 90 degrees, because sine pi over 2 is 1 divided by cosine pi over 2, 0. 1 over 0 gives us infinity. So that would be pi over 2 minus arctan 1. Arctan 1 means sine equal cosine. In such case, the angle would be pi over 4, 45 degrees. Hence, the answer is pi over 4 and it converges. Okay? However, there happens to be another way in order to find or to check the convergence of this integral. Let's recall into mind the p series. When you have 1 over x to the power of p, this would be a p series having a condition that when p is greater than 1 strictly, then 1 over x to the power of p converges, meaning that it has a finite limit. Now, here by comparison, 1 over x squared plus 1 is less than 1 over x squared, given that the denominator is larger because it has one value added to it. Okay? Hence, given that 1 over x squared dx, integral from 1 to infinity, converges, this implies the convergence of also 1 over x squared plus 1. And after that, we evaluate that actually this has already been done. So the value of the integral is equal to pi over 4. Integral from 0 to infinity of e minus x sin x dx. Okay, so if we want to, let's say u is equal to e minus x du equal minus e minus x, dv equal sin x, v equal minus cosine x. So basically, yeah, this is of the form of u dv. Let's solve it this way. It is equal to uv, or e minus x, times minus cosine x, minus integral of v du, which is minus cosine x times minus e minus x. Okay, minus minus plus, and we are left with 1 minus here, so minus cosine x times e minus x dx. Then again, let's suppose u is equal to e minus x, du equal minus e minus x, dv equal, for this integral, okay, we're gonna call this j, and the first one I, the main one. dv equal minus cosine x, v equal minus sin x. So j is equal to uv, which is minus sin x e minus x, minus integral of v du. So minus minus minus, minus and minus plus, we end up with 1 minus sin x e minus x, which is I. That's the original integral. So let's fill it in within this equation. Erasing a little bit. We want to fill j with its original, or with its solved value, which is this. So I, this is the main integral, is equal to minus cosine x e minus x plus j, which is minus sine x e minus x, minus integral of sine x e minus x. What is integral sine x e minus x? This is I. Okay, so minus I. Hence, this minus I can be removed to the left. It becomes plus I, so 2I is equal to minus cosine x e minus x minus sine x e minus x. Now, okay, so minus I can, I becomes 1 over 2, minus 1 over 2 of cosine x e minus x plus sine x e minus x, or minus e minus x over 2 as a common factor, cosine x plus sine x. And this is the answer. Again, we have integrated twice, okay? So we end up with minus 1 over 2 e minus x sine x plus cosine x. Now we are integrating, okay, so this is, as a reminder, this is the limit as b approaches infinity of minus 1 over 2 e minus x times sin x plus cosine x between b and 0. So for b approaching infinity, e minus infinity is 0. So this entire thing becomes 0. As for x is equal to 0, you have cosine 0 is 1 plus sine 0, so 0, 1 times e to the power of 0 is 1 times minus 1 over 2, okay? Now, so this is, again, this is f of b minus f of a. F of b is 0 minus f of a, which is minus 1 over 2 e 0 equal plus 1 over 2. Evaluate integral from 0 to 1 ln x dx. Now, given that ln 0 blows up, we need to use the method of the limit. So this becomes limit as a approaches 0 plus integral from a to 1 ln x dx. Okay, what is integral ln x dx? This is equal limit a approaching 0 plus x ln x minus x between 1 and a equal ln 1 0, so and minus x is minus 1 minus a ln a minus a. Okay, so a here 0, okay, doesn't matter. A to the left is 0. ln 0 is minus infinity, so this is 0 times minus infinity, correct? So 0 times minus infinity is 0. We end up with minus 1 as a final answer. So again, integral of ln x dx gives us x ln x minus x and x ln x minus x between a and 1, okay, or 1 and a, 1 being the upper bound, a the lower bound, as a approaches 0 plus. So this is equal to 1 ln 1 minus 1, which is, by the way, we end up with minus 1, minus a ln a minus a. Okay, limit as a approaches 0 plus of a ln a is equal to 0. So we are left with minus 1. Integral from 0 to infinity xe minus x dx. Now here I'm going to use a different approach, which is the differentiation of one component and integration of the other. Tabular solution, okay? So x to the left and e minus x to the right. We can also use the integration by parts, but this would be, for me, a little bit easier. So derivative of x is 1, then of 1 is 0. As for e minus x, it is minus e minus x, then plus e minus x. And you multiply like this, while alternating the signs. So first one, the sign is plus, second time, it would be minus, etc. Here, we only have two multiplications because we already had reached 0. So this is equal to minus xe minus x minus e minus x as an integral. Now to solve it, this is equal to the limit, since you have infinity here, of b approaching infinity, integral from 0 to b xe minus x dx equal minus xe minus x minus e minus x between b and 0, which is minus b e minus b minus e minus b minus, okay, so here you have 0 times e minus 0. E0 is 1, but 0, the first component, minus e minus 0, which is minus 1. Okay, you have minus on the outside, so minus minus 1, correct. Now, as b approaches infinity, e minus b becomes 0, and e minus b here also, e minus infinity is 0, so we are left with plus 1. And here's the solution. Integral xe minus x dx is equal to minus x plus 1 e minus x. Evaluating from 0 to infinity gives us 1. Integral from 0 to infinity cosine x dx. Now, integral cosine x dx without the bounds gives us sine x plus c. Given we have these bounds, so it is the limit as b approaches infinity of sine x between b and 0 equals sine b, because sine 0 is 0, and this is limit of sine b as b approaches infinity. which is divergent. Okay, there's no limit, so it blows up. It keeps oscillating between 0 and 1, so there's no limit. It's not convergent. And this is the solution, as we mentioned, given that B keeps changing. Okay, it's like an angle that keeps rotating. So there's no actual limit. Sin B, the sinus of B, does not even exist as a constant value. It keeps changing as B evolves. Therefore, the limit does not exist and this integral diverges. Evaluate integral of x to the power of minus 2 over 3 dx. So, without the bounds, this is minus 2 over 3 dx equal x to the power of minus 2 over 3 plus 1 over minus 2 over 3 plus 1, which is equal 3 minus 2, okay, x to the power of 1/3 divided by 1/3 or equal to 3. This is the third root of x. Now, let's evaluate the limit. Okay, so this is equal, this entire integral is equal to the limit as a approaches 0 plus of integral from a to 1 x to the power minus 2/3 dx. So limit a approaching 0 plus of 3/3 root of x between 1 and a equal limit a approaching 0 plus. Okay, so this is 3 minus 3/3 root of a being 0, okay, equal plus 3. And this is the solution. 3 times third root of x between 1 and 0 equal 3. Determine whether integral from 0 to 1 x to the power of minus 2 dx converges. Now I can say it probably does not converge just by looking at it. So this is equal to, first, without bounds, integral of x minus 2 dx, which is equal to x minus 2 plus 1 over minus 2 plus 1, or x to the power of minus 1 divided by minus 1 equal minus 1 over x plus c without bounds. With bounds, this becomes the limit as a approaches 0 plus of of minus 1 over x between 1 and 0, between 1 and a rather, equal minus 1 minus 1 over a for a approaching 0. Now, as a approaches 0, okay, this becomes infinity. This entire term blows up to infinity. Hence, this integral diverges automatically. So here's the final solution. This is equal to a limit as a approaches 0 plus of minus 1 over x between 1 and a equal limit of minus 1 plus 1 over a as a approaches 0 plus, and this part blows up to infinity. That's why the integral diverges. Integral from minus infinity to plus infinity of 1 over 1 plus x squared dx. Now, this integral without bounds is equal actually to arctan x. Okay, so limit of arctan x, which becomes between plus infinity and minus infinity. So what is that? Okay, The angle that gives us infinity is actually 1 over 0 for the tangent. So it is for sine, it should be 1, and cosine should be 0. What is that angle? Okay, because remember, the tangent theta is equal to sine over cosine. This 1 over 0 is what blows up to infinity. So for which angle we have such behavior? For pi over 2, correct? So it is pi over 2 minus, now, for which angle we get minus infinity? So that would be minus 1 over 0, which is minus pi over 2, okay? Because the sign of minus pi over 2 minus 90 degrees would be negative. Hence, it is pi over 2 minus pi over 2 equal pi over 2 plus pi over 2, or plus pi. And here's the answer, as we mentioned. It's pi over 2 minus pi over 2, so plus pi. Because again, remember, tangent theta is equal to sine theta over cosine theta. Only when the denominator is 0, it blows up to infinity, and in such case, sine theta would be 1, okay? That angle would be pi over 2. That's why. For the angle being minus pi over 2, it becomes minus 1 over 0, which gives us minus infinity. Evaluate integral from 0 to infinity x2 e minus x dx. Now here, the tabular solution would be the best one. So again, you take x squared, and we differentiated, and for e minus x, we integrated. Why we differentiate x squared? Because this is the only component within this integral that actually degenerates all the way to a constant and then to 0. As for e minus x, it remains constant. It always reproduces an exponential as you integrate. Hence, let's differentiate x squared, so it becomes 2x, 2, then 0. As for e minus x, this is minus e minus x, then plus e minus x, then minus e minus x. And you multiply with an alternating sign, so plus minus and plus. Hence, the solution of the integral x squared e minus x dx gives us minus x squared e minus x, which is this one, then minus 2x e minus x, okay, this component, then plus minus e minus x times 2, which is minus 2e minus x. Now, this integral is equal to the limit as b approaches infinity, integral from 0 to b x2 e minus x, which is this entire quantity above, e minus x minus 2e minus x, between b and 0. Okay. Let's replace the limits. So, okay. First, minus b squared e minus b minus 2b e minus b minus 2e minus b, and this is e minus infinity, so the entire thing becomes 0, minus, we replace x with 0, so first term cancels out, second term cancels out, and we are left with minus 2e 0. e0 is equal to 1, so the answer is plus 2. Integral from 1 to infinity of 1 divided by x3 over 2 dx. First, let's solve it as a classical unbounded integral. And we move x3 over 2 to the numerator, so it becomes x minus 3 over 2 dx equal x minus 3 over 2 plus 1 divided by minus 3 over 2 plus 1, which is equal to minus 3 plus 2, so x to the power of minus 1 half divided by minus 1 half equal minus 2 times x to the power of minus 1 half equal minus 2 divided by x to the power of 1 half, which is square root of x. So this is equal to the limit as b approaches infinity minus 2 over square root of x between b and 1 equal minus 2 over square root of b minus 2 over square root of 1. Now, as b approaches infinity, minus 2 over square root of b approaches 0. So we end up with minus 2, which is plus 2. So it converges. That's the final answer. So minus 2x to the power of minus 1 half between infinity and 1 equal 2. Integral from 0 to infinity xe minus 2x dx. Let's solve it by using the substitution method. So let u be equal to x, du equal dx, dv equal e minus 2x, hence v equal minus 1 half e minus 2x. So let's consider that this is an unbounded integral at first. Integral xe minus 2x dx is equal to uv minus integral of v du. Okay? So the form is the following. Integral u dv equal uv minus integral of v du. So this is equal to minus x over 2, this is uv, e minus 2x, minus integral of v du, minus minus is plus. So plus 1 half e minus 2x, du is dx. Okay, equal minus x over 2 e minus 2x, and integral of 1 half e minus 2x gives us minus 1 4 e minus 2x. We pull this here and we need to evaluate the limit as b approaches infinity of minus x over 2 e minus 2x minus 1 over 4 e minus 2x between b and 0. Okay, now for b, e minus infinity on both sides is 0, so it cancels out. Minus, for x equals 0, this part becomes 0 here, and you are left with minus 1/4 e0, which is 1. e0 is equal to 1. Hence, it is equal to 1 over 4. And this is integration by parts again. Yeah, it's called integration by parts rather than substitution. And we end up with 1 over 4. Evaluate integral from 0 to infinity of x divided by 1 plus x squared dx. Okay, here we can use the u substitution. So let's say u is equal to 1 plus x squared. du is then equal to x dx. Hence, x dx is equal du divided by 2. So if we want to solve it as a normal integral, so integral of x dx is du divided by 2. And in the denominator, this is u, 1 plus x squared is u squared. Okay, equal to 1 half integral of u to the power of minus 2 as we move it to the numerator, du, which is equal 1 half times u minus 2 plus 1 over minus 2 plus 1 equal u minus 1 over minus 1. This is equal minus 1 half times 1 over u. Let's flip u back into its original value. So it is minus 1 half times 1 over 1 plus x squared. Okay, let's evaluate the limit as v approaches infinity of minus 1 half, okay, which is minus 1 over 2 multiplied by 1 plus x squared between b and 0. Now, as you replace with b, so as like b, okay, x squared for x equal infinity, this blows up and becomes minus 1 over infinity, which is 0. Not blows up, actually the denominator blows up, but the entire thing goes to 0. Minus, okay, replacing 0 in the denominator, we end up with minus 1 over 2, which is plus 1 over 2. And this is the solution. So let u equal 1 plus x squared, du equal to x dx. Then we replace them back in the integral. We end up with 1 half integral from 1 to infinity, u to the power of minus 2 du, which is 1 half minus 1 over u between infinity and 1. And it gives us 1 half. Derive a reduction formula for in equal integral n to the power of nx dx. Now, sin to the power of nx can be written as sin to the power of n minus 1 x times sin x. Okay, so let's use the integration by parts. U equal sin n to the power of minus 1 x, dv equal sin x dx. So du becomes n minus 1 sin n minus 2 x times cosine x dx. Okay, so it is n minus 1 sin n minus 2 x times cosine x times the derivative of sin x dx, and v is equal to minus cosine x. Clear? Applying the integration by parts, in is equal to minus sin to the power of n minus 1 x cosine x, which is uv by the way, minus integral of v du, plus n minus 1 times sin n minus 2 x cosine x times cosine x, okay, which is v du by the way, times minus cosine x. So this is, okay, minus cosine x times sin n to the power of minus 2, and you have minus on the outside, but with this minus of minus integral v du, it becomes plus. This is why you have n minus 1 positive sin n to the power of minus 2 x times cosine x times minus cosine x dx. So cosine squared x, and the minus is removed by this minus behind the integral. Using cosine squared x is equal to 1 minus sine squared x. So we obtain in is equal to minus sin to the power of n minus 1 x cosine x plus n minus 1 in minus 2 minus n minus 1 in. Therefore, nin is equal to minus sine n minus 1 x cosine x by substitution here, plus n minus 1 in minus 2. Hence, in is equal to minus sine n minus 1 x cosine x divided by n plus n minus 1 over n minus 2. Use the reduction formula to evaluate integral of sine to the power of 4x dx. This is the formula. So in, which is I4, is equal to minus sin of n minus 1, which is 4 minus 1, or 3x, times cosine x divided by n, which is 4, plus 3 over 4, which is n minus 1 divided by n, times in minus 2, which is I2. Okay, so what is I2? Meaning for sin square x. It is equal to minus sin x cosine x, also the same formula, that would be n minus 1, so 2 minus 1 sin x cosine x divided by 2, plus 1 over 2 n minus 1 over n times x, okay, which is yeah, I2 or sin 0, okay, so to the power of 0 plus 1 over 2x. Substituting back, we get this solution, minus 1 over 4 sin 3x cosine x, minus 3 over 8 sin x cosine x plus 3 over 8x plus c. Jn equal cosine nx dx. Cosine nx also can be written as cosine to the power of n minus 1 x times cosine x. Let's solve it. U equal cosine n minus 1 x, dv equal cosine x dx. After simplification, you get Jn equal sine x cosine n minus 1 x over n plus n minus 1 over n Jn minus 2. Using the same formula, integrate cosine 5x dx. So this becomes n minus 1, correct, which is sin x times cosine n minus 1x over n plus n minus 1 over n, which is 4 over 5, j3. Now j3 is, okay, sin x cosine 3 minus 1 is cosine square x divided by 3 plus n minus 1 for n equals 3, which is 2, divided by 3, j1. What is j1? It is sine x, following the same process. And we obtain the final solution, which is the following. Derive a reduction formula for in equal integral x to the power of n ex dx. Okay, so let's use the tabular method. We derive or differentiate the first component and integrate the second. Now the second would always remain ex, by the way. As for the first, it becomes n xn minus 1, then n times n minus 1, xn minus 2, etc. Okay, so this is plus minus, it's equal to xn ex minus n times x to the power n minus 1 ex. Okay, or using integration by parts, so u equal xn, du equal n xn minus 1, dv equal ex, v equal ex. So it is uv xn ex minus integral of v du, which is ex, times n xn minus 1 dx. So you can remove n to the outside and becomes integral of in minus 1 basically. Hence, so u equal xn, dv equal ex dx, du n xn minus 1 dx, v equal ex, in is equal xn ex minus n integral xn minus 1 ex dx, which is in minus 1. Using the reduction formula to evaluate integral x3 ex dx, so I3 is equal to x3 ex minus 3i2, I2 equal x squared ex minus 2i1. Using the same formula, I1 equal x ex minus I0, and I0 is equal to ex. So substituting backwards, you get ex times x3 minus 3x squared plus 6x minus 6 plus c. Deriving a reduction formula for in equal integral ln x to the power of n dx. U is equal to ln x to the power of n, du is equal to n ln x to the power of n minus 1, divided by x. Why? Because it is n ln x times n minus 1 times the derivative of ln x, which is 1 over x. This is the formula. This is the chain rule. dv equal dx, v is equal to x. Therefore, in is equal to x ln x to the power of n minus n integral ln x minus to the power of n minus 1 dx, which is, by the way, in minus 1. Let's evaluate this integral using the same concept. So, I2 is equal to x ln x squared minus 2i1. I1 equal x ln x minus x. Hence, by substituting, you get x ln x squared minus 2x ln x, which is minus 2i, minus 2 minus x, which is plus 2x plus c. Using the reduction formula, let's solve this integral. So in is equal to n minus 1 over n times in minus 2 for definite integrals over 0 to pi over 2. Since I1 equal 1, it resolves into 8 divided by 15. Okay, so this is the solution for that. As for cosine to the power of 6x dx, integral from 0 to pi over 2, let's solve this one. So j6 is equal to 5 over 6 j4, j4 3 over 4 j2, j2 1 over 2 j0. j0 equal pi over 2, j6 is this quantity 5 pi over 32. Tangent powers, in equal integral of tan to the power nx dx. So what does it resolve into? Now, tan square x is equal to secant square x minus 1. We know that. So in is equal integral of tan n minus 2 x, okay, times secant square x minus 1 dx, because we are resolving tan to the power of nx dx. Hence, in is equal to tan to the power n minus 1 x divided by n minus 1 minus in minus 2. Of course, after developing it, he came to the conclusion. But here, what is relevant is using this formula to solve tan 4x dx, for example. So I4 is equal 1/3, which is 1 over n minus 1 times tan 3x n minus 1 minus I2. I2 equal 10x minus x. So it becomes 1/3 10 to the power of 3x minus 10x plus c. Let's evaluate integral from 0 to infinity x4 e minus x dx. Using that same rule we figured out before. In is equal to n minus 1. I4 equal 4 factorial equal 24. Okay, as simple as that. N times in minus 1. Using reduction formulas to evaluate x4 ex. So ex times x4 minus 4x3 plus 12x squared minus 24x plus 24 plus c. Use a reduction formula to evaluate integral x squared ln x. So u equal ln x dv equal x squared dx, du equal 1 over x, v equal x3 divided by 3. So uv minus integral of v du, x3 over 3 ln x minus x3 over 9 plus c. Integral sin 6x dx, so I6 is equal to minus 1 over 6, which is n, sin 5x, or sin to the power of n minus 1, times cosine x, plus 5 over 6 I4. We keep continuing until we get I0 equal x, so we obtain this solution. Thank you for watching, and I hope that you enjoyed this session, and see you next time.